All right, let's talk about nuclear energy. We're going to crack open the atom itself to really understand one of the most powerful and, controversial forces we've ever harnessed. Today, we are demystifying the whole thing by looking at the two completely different ways you can unlock that energy. All right, let's talk about nuclear energy. We're going to crack open the atom itself to really understand one of the most powerful and, controversial forces we've ever harnessed. Today, we are demystifying the whole thing by looking at the two completely different ways you can unlock that energy. Fission versus fusion.
It really all boils down to the most famous equation in all of science, E equals mc squared. And the real secret here, the mind-blowing part, isn't the E for energy or the m for mass. It's the c squared, the speed of light, times itself. That is a gigantic, almost unimaginable number. It means that a tiny, tiny speck of matter can be converted into a truly staggering amount of energy. And that one single idea, well, that's the engine behind everything we're about to discuss. So how do you actually put that incredible equation to work? Well, it turns out there are two basically opposite ways to do it. On one side, you've got fission. That's where you take a big, heavy atom and you split it apart. This is the tech that powers every single nuclear plant on Earth right now. And on the other side, you have fusion. This is where you take two super light atoms and you slam them together. This is what powers the sun, and it's what we're all hoping will power our future.
Okay, so let's start with fission. To really get how we're making carbon-free electricity today, you have to understand the elegant, controlled dance that is a nuclear chain reaction. The whole process kicks off with a very specific kind of fuel, uranium. But here's the catch. Not just any old uranium will do. Most of the uranium you dig out of the ground is an isotope called U-238, and it's pretty stable. The magic ingredient, the stuff we actually need, is U-235. It's fissile, which is just a fancy way of saying it's easy to split. The problem? It makes up less than 1% of all the natural uranium on the planet. So it's incredibly rare and incredibly valuable. So how does this actually work? Just picture a set of cosmic dominoes. You start by shooting one tiny little particle, a neutron, at one of those U-235 atoms. It hits, and boom, the atom splits apart, releasing a massive burst of energy. But, and this is the crucial part, it also spits out 2 or 3 brand new neutrons. Those neutrons then fly off and smash into other U-235 atoms, which split, release more energy, and, you guessed it, more neutrons. That's it. You've created a self-sustaining chain reaction. But hang on a second. A rapidly expanding, out-of-control chain reaction? Well, that's the recipe for an atomic bomb. So how in the world do you take that same ferocious power and use it to, safely boil water and generate electricity? This is where the real genius of nuclear engineering comes into play. Okay, now here's something that sounds totally backwards, but it's absolutely key. To make the chain reaction go faster and be more efficient, you have to slow the neutrons down. Yeah, you heard me right. The neutrons that fly out of a split atom are actually moving too fast to be reliably captured by the next atom. So reactors use something called a moderator, which is usually just plain old water, to act like a speed bump. By slowing those neutrons down, you make them way more likely to cause the next split, which effectively acts as the accelerator for the whole system. So, if the moderator is the gas pedal, then the control rods are the brakes. It's that simple. These are rods made of materials like boron, which are just fantastic at soaking up neutrons like a sponge. Operators can raise or lower these rods into the reactor core. You lower the rods in, they absorb more neutrons, and the reaction slows down. You pull them out, and the reaction speeds back up. This is how you get precise minute-by-minute control over all that power. But, of course, with all this power comes some very serious responsibilities. And we absolutely have to talk about the two massive challenges that really define the whole public debate around fission: the risk of major accidents and the problem of what to do with the waste. The history of nuclear power has been marked by 3 major well-known accidents. You have 3 Mile Island in '79, Chernobyl in '86, and Fukushima in 2011. Each was a disaster. and each was caused by a very different mix of things: equipment failure, flawed designs, human error, or just an overwhelming natural disaster. And from each one, the entire world learned some incredibly hard lessons, which led to huge improvements in safety designs and operating rules. And then you've got the second big problem: the waste. The used nuclear fuel from a fission reactor stays dangerously radioactive for thousands upon thousands of years. I mean, just think about that. How do you design a container and a storage site that you can guarantee will be safe for a timescale that's literally longer than all of recorded human history? It's one of the greatest technical challenges we face.
Now, those big challenges with fission are exactly why so many brilliant scientists have been chasing a completely different dream. So let's flip the script. We're going to shift our focus from splitting atoms apart to jamming them together and look at the incredible promise of fusion.
See, if fission is a human invention, fusion is just nature's own recipe for power. Deep inside the core of our sun, the crushing gravity and insane temperatures are constantly slamming light elements like hydrogen together to create helium. In the process, it releases the energy that has lit up our solar system for billions of years. What we're trying to do is literally bottle a star.
So why would we even try to bottle a star? The payoff is just enormous. Let's just compare the pros here. Fission's biggest advantage, as you can see, is that the technology is established, it works today. But now look at fusion's potential. First, the fuel source is basically limitless. You can get it from seawater. And second, it's so much cleaner. There's no long-lived, high-level radioactive waste to worry about for millennia. The promise is so huge, it's a total game changer.
Okay, this all sounds incredible, right? Limitless fuel, cleaner power. So the obvious question is, why don't we have it yet? If it's so great, where are the fusion power plants? Well, the answer is that it's one of the single greatest scientific and engineering challenges humanity has ever taken on. The heart of the problem is just one thing: heat. You see, atomic nuclei are all positively charged, so they naturally push each other away. To overcome that force and smash them together, you need temperatures that are just, well, they're hard to even think about. We're talking over 100 million degrees Celsius. That's not just hot. That is many, many times hotter than the core of the actual sun. Which, of course, leads to the ultimate engineering question. How on earth do you contain something that hot? I mean, what kind of box do you build for it? Any physical material? Any metal? Any ceramic? It would just instantly vaporize. You can't just build a container. The solutions scientists are working on are straight out of science fiction. There are two main paths. The first is called magnetic confinement. This uses incredibly powerful magnetic fields to create a sort of invisible bottle, trapping the superhot gas, or plasma, so it floats in the middle of a chamber, never touching the walls. The second path is inertial confinement. This is like a tiny Death Star. You take a huge array of the world's most powerful lasers, and you fire them all at once at a tiny little fuel pellet, crushing it so fast that it fuses before it even has a chance to blow apart. Now, both of these incredible, mind-bending projects, they share the exact same goal. It all comes down to achieving one thing: ignition. That is the holy grail of fusion research. Ignition is that magical tipping point where the fusion reaction itself starts producing more energy than we have to keep pumping in to get it started. It's the moment we create a tiny, self-sustaining star right here on Earth. So, all of this brings us right back to where we are today, and to the fundamental choice we have to make when we talk about nuclear energy for our future. Let's just lay it all out one last time. You've got fission, which splits heavy atoms. It's a technology that works, it's commercially viable, and it gives us huge amounts of carbon-free power right now. But it comes with the undeniable risks of accidents and long-term waste. Then you've got fusion, which joins light atoms. It's still experimental, and its biggest risk is simply, well, can we actually pull it off? Is it even scientifically feasible on a commercial scale? But its promise is for an even cleaner, even more abundant source of power down the road. And that leaves us with this final critical question. As we face this massive challenge of needing more and more energy, but also needing a stable climate, how do we choose? Do we embrace the proven power of fission and focus on managing its risks as best we can today? Or do we bet big on the dream of fusion
that cleaner, almost perfect energy source that might still be decades away from reality. That's the choice we face.